Hello, today we want to solve two new inequalities. So Cauchy's inequality provides us with an upper bound for a sum of pairwise products. And of course, it's very natural to assume that there's also an upper bound for the sum of products of three or more terms. So let's take a look at the second inequality. Let's try to prove the first one first. So let's write out the left-hand side just without the potentiation to form. If we group the bk and ck, we can do a Cauchy inequality considering that these two terms are just one term, and say, okay, that's the inequality that's smaller or equal to ak squared over 1/2 times the summation of bk ck from 1 to n. There's a squared here, of course, to the power of 1/2. Okay, so let's do a side calculation. Let's sum the right term. So it's 1 from n of bk squared ck squared. We can basically write out this term as bk squared and ck squared. We don't have to multiply them and then square them. So all of this to the power of 1/2. This is smaller or equal. If we apply the Cauchy-Schwarz inequality with respect to bk squared and ck squared, we get the following. This summation from 1 to n, bk squared and then to the power of 2, and all of this to the power of 1/2 times the summation of ck squared. Of course, this is also squared from 1 to n into the power of 1/2. So far we only estimated this sum. Now we also have to take all of this term and write to the power of 1/2 because we didn't change that part. Okay, so we want to remember that what the Cauchy-Schwarz inequality tells us. So we have a summation of xk times yk from 1 to n. This is smaller or equal to the summation of xk squared from 1 to n to the power of 1 over n times the summation of yk squared from 1 to n to the power of 1/2. And of course, we can insert in the xk and yk whatever we want. And in our case, our entire bk squared was xk, and our entire ck squared was yk. And so we had the xk squared, or in other terms, the bk squared was then squared. So you just have to insert the definition very carefully. So let's just write this out for the, did a mistake here actually. This is just xk, it's not xk squared. So this is yk. Okay, anyway, so we want to continue with our estimation. Let's continue here. So the first part stays the same. It's from 1 to n, ak squared, and this is to the power of 1/2 times. Now we use the green part because we already estimated the second part. So this is just summation from 1 to n, bk to the power of 4, because squared again is just to the power of 4, over, so we have here above 1/2, which is multiplied with 1/2 because that's how potentiation works. So we have 1 over 4 times summation of ck to the power of 4 for the same reason, and then to the power of 1 over 4. There's actually no reason to do this side, this bigger bracket, because we wanted to do this in multiple steps, but I think we don't need to. So what did we use here? We used this inequality here to estimate the second part. Yeah. Okay. So what did we show? We showed that the summation of ak, bk, ck from 1 to n is smaller or equal to the summation of ak to the power of 2 from 1 to n to the power of 1 over 2 times the summation of bk to the power of 4 from 1 to n to the power of 1 over 4 times the summation of ck to the power of 4 from 1 to n to the power of 1 over 4, which is of course equivalent to the inequality above. We can also just say, okay, that we take the whole inequality to the power of 4, so then, oops, this cancels out, it becomes just 1, and this to the power of 4 becomes, of course, 2, which is, of course, matching what we have here. When we take to the power of 4, we have the power of 4 on the left-hand side, we have a 2 here, and a 1 and a 1. So this is also okay. And we're done with the first inequality. Now we're ready to tackle the second inequality. So the second inequality is just a generalization of the Cauchy-Schwarz inequality, just for more than two terms. 1 to n. And do we want to square it or not? Yes, we want to square it. All of this to the power of 2, which is smaller or equal to summation of ak to the power of 2 from 1 to n to the power of 1/2 times summation of bk from 1 to n to the power of 1/2. Oh, then we missed a square here. Times, now the last term, 1 over n times ck to the power of 2 to the power of 1 over 2. So what we want to do now is to define this as big C, and we define a new sequence, ck bar, as ck divided by c. Now we want to show that the summation of ak, bk, ck from 1 to n is smaller or equal to the summation of ak to the power of 2 from 1 to n. Oh, actually there's no 1/2 here. That's a mistake. It's not deleted. Why is it? Whatever. Okay. So, okay, that's, and then the summation of 1 over n to n bk to the power of 2. And, oh, there would be like a bar here. We have here to the power of 2. Why would this suffice? Because basically what we did was to just take the whole c and then divide it in the inequality. So we just took this c and we brought it to the left-hand side, and then we sneaked it into the ck and divided it by c. And just thinking about it, it's actually more convenient in our case to write it without the square to the left-hand side and to actually bring them back. So we either have potentiate with 1 over 2 on the left-hand side or with 1 over half. So it's either a square root on the right-hand side or a square on the left-hand side. Let's do it actually like this because that's more convenient in some calculations. Okay. In terms of like y, let's just show this in a more obvious way. So if we insert here our definition, this is just ck divided by c, and then we say, okay, we have a summation of ak, bk, ck from 1 to n, and that's smaller or equal to, no, that's not just ck, that's divided by c. Let's remove the y here and just show that this is basically equivalent to the summation of ak squared from 1 to n, 1 over 2, to n bk squared to the power of 1 over 2. And that is equivalent to just the summation of ak, bk, and then ck, and smaller or equal to the summation of 1 n ak squared to the power of 1 over 2 times the summation from 1 to n of bk squared to the power of 1 over 2 times c. So we just took the c and then we multiplied it upwards to the right-hand side because it's a positive constant, and yeah, it's a constant, so we can just pull it out of the summation and multiply it to the right-hand side. Yeah, and the c was exactly like this term, including the 1 over 2. So it's also square root. Yeah, and that shows us that that is the original inequality. Okay, so to show this, the last inequality, which is what we want to show, we just have to show the first one that we said. Okay, let's write it again and observe why it has to be true. We have ak times bk times ck. This is the ck bar, sorry. This is always smaller or equal to 1. Why is it that way? Because it's defined as ck divided by c. Because ck bar is ck divided by c. And what is c? C is just summation from 1 to n of ck squared to the power 1 over 2. So it actually has, well, maybe we should use a different running index. Let's do ci. And yeah, that's clearly bigger than the ck on its own. It's not equal to 1. Okay. So the summation ultimately is smaller or equal to ak times bk from 1 to n times 1, but we can just ignore that, just times 1. Okay, now we apply the Cauchy-Schwarz inequality to this summation, and then we get summation from 1 to n, ak, oops, of ak squared to the power of 1 over 2 times the summation of bk squared from 1 over to the 2 to the power of 1 over 2. Yeah, and that was exactly what we wanted to show. This is the inequality. We started out with this term and ended up showing that it's smaller or equal to this term, which is what we wanted to show. And we also showed why we wanted to show this, because we showed that this inequality is equivalent to our original definition, our original question with the c, which is the c is just a placeholder, basically, just to move it around. Yes, and that was exactly our inequality. Okay, I think that was a bit more difficult than the previous inequalities, but nevertheless manageable. I think it requires a few prerequisites to understand, but overall quite manageable. Okay, see you next time.